So we're going to talk about galvanic cells and electrochemical series. And the reason I've got spontaneous reactions up the top is because a galvanic reaction is a spontaneous reaction, or what happens in a galvanic cells. And basically, a spontaneous reaction is one that can proceed on its own. You don't need to apply any sort of external energy to it for it to occur. You put the right components in, and the reaction will start. So a simple example of that, and it's like a precursor to actually using a galvanic cell, is this reaction here, where I've got zinc metal, which is like I've got here, and I've got some copper sulfate solution there. And when they're together, the zinc will donate 2 electrons to the copper, and the result is the zinc now forms the zinc metal, because it's released those 2 electrons, is got zinc 2+, and you've got copper sol left over, and that's sort of what's happening here in that example. And this is shown as like a diagrammatically. This is what the reality looks like here. All right, so let's move on to galvanic cell design. So when we got a galvanic cell, now keep in mind the first one of these was really the Daniell cell, and that used zinc metal and copper ions to produce electricity. Now when we draw these, let's draw them as, got 2 beakers for sake of argument. Now let's go, we've got some aqueous solution, so we've generally got some electrolyte in here. So if I put here, I've got some sort of electrolyte here. Remember, electrolyte is a liquid that can conduct electricity. What I want to do in here is to connect both of these cells, both of the solutions together there, and I'll use a salt bridge to do that. And that provides a supply of mobile ions that carries charges between them. So you're going to have charges flowing up there and going through like that. And if I get rid of those ones for a sec, and then in the same manner, let's pick a different color. I'm going to have ions that go up and travel through there as well. Okay, so that's the sort of general idea of what a salt bridge is doing. It's allowing for those movement of charge between the cells. And now this part here is really what we would call the inner circuit. So that's our inner circuit here that we've talked about. We're talking about what's in a half cell. So what else we've got in a half cell? What else we've got is going to be our electrodes. We go into those in a bit more detail in a moment. So we've got an electrode. So that's a solid that is used to conduct electricity in a galvanic half cell, and we're going to connect some wires to it. Now we usually have some sort of thing there, whether it's a voltmeter or an ammeter or something like that. Okay, but that's what we've got. So you need to be able to draw something like this and then be able to label it according to what's there. So we're going to talk about the anode now. Now this is, I'm going to get rid of a few things here just because they're taking up space. Okay, now when we're looking at that, if this is a negative charge, that means that's the anode. Oops. And if it's at the anode, what's occurring at the anode is oxidation. So oxidation is occurring here. And what oxidation is, if you think oil, as in oxidation is loss, so you're actually losing electrons. So you're actually going to have electrons flowing in this direction. Okay, and that means this is positive over here. So now we're talking about the cathode. It's where reduction is occurring. So reduction is occurring here. Now when you actually draw these and get questions, they could actually go both ways, but for the moment I'm just showing it like this. And remember, that's rig, reduction is gain. Reduction is gain, and that's where you're actually, the electrons are coming to and things are happening there. So I won't try to draw too much more here because it's going to get really, really messy. But in this process, that generates electrical energy because we've now got that flow of electrons, flow of charge, and then we've got flow of charge both ways for the ions there. So that's the basic idea of how electrochemical series will work, and that's how you can sort of look at it as well. So keep in mind at the anode, good point to keep in mind here, if the reducing agent, so the reducing agent is the one that's been oxidized, is a metal, it's going to be used up. So if this was, say, zinc, then as the electrons are being moved away into solution, you're going to get the zinc 2+. Okay, and as you come in around to the cathode, I should have actually written cathode here before. All right, what you're going to have is the negative electrons are drawn to this, and then you're going to have, say, for example, copper 2+, and the copper 2+ ions are going to be drawn to here, and what you'll get is the electrons interacting with that and forming copper. So that's the idea. So this is another way of showing that, and as you can see, there's been movement of ions there in your salt bridge. That's just usually a potassium nitrate. That's usually seen as being the easiest one to use, and it's just important that whatever salt that's used in the salt bridge is not going to react with the chemicals in the beakers. So you want it as something that's not going to form any become insoluble with any components. Okay, so when constructing answers, remember the internal circuit always involves ions. Remember that would be this bit here, and even parts of it in here. The external circuit involves the electrons. That's this bit here. Red cat, reduction always occurs at the cathode. That's here. And oxidation always occurs at the anode. So remember, oxidation is lost, so it's losing electrons there. So keep in mind some of the half cells you can get. It's not always going to be a metal electrode. Like, for example, this is the sort of the example we've just been talking about. You've got your electrical wire, you've got your metallic zinc electrode, could be something else, and that's how it would look. If you've got a solution half cell, what you're going to have is some inert substance. That's usually either graphite or platinum. I know it's a metal, platinum's a metal, but it's seen as inert. So you're going to have something from solution go into here to look at that, have the electrons being oxidized from that. So examples, so you can have Fe2+. The other way is to use a gas non-metal iron half cell. So you've got some sort of inert electrode there. You've got some, so for example, chlorine bubbled through, and then you've got some chlorine in the solution. Okay, and we'll go into more details of those later on. Now let's have a look at the electrochemical series now. All right, so clearly this is not the full electrochemical series. It's just what we're going to use for the moment as a sort of a starting point. Okay, and it's what we've been working with. We've been working with the copper and the zinc. Now, when we look at something like this, is sort of what's happening. It says the buildup of negative charge on the zinc is greater than the copper due to it being a stronger oxidizing agent and more inclined to lose electrons. So slightly take back what I just said. I'm going to read that and fix it up, because that's actually a little bit wrong there. The buildup of negative charge on zinc is greater than copper due to it being a stronger reducing agent. Because remember, zinc is undergoing oxidation, so it's not an oxidizing. It's a stronger reducing agent and more inclined to lose electrons. So that's what we're seeing here. We're seeing all those electrons being there because essentially these positive charges are heading off that way, and the electrons are flowing through to here, where these 2+ ions from, say, the copper would be attracted to the electrode, and that's where you're moving that, moving it around like that. So let's have a look at standard electrode potentials. Again, here's a modified version of the electrochemical series. We'll get the full one shortly. But what we need to look at here is that the flow of electrons created by these different half cell combinations. So we could have different half cell combinations here. All right. They vary and can be, you can measure with a voltmeter. We get a cell potential difference, which is sort of like the voltage. So what we can't do is measure that electric potential from an individual electrode or electrolyte's half cell directly. So what we do is we standardize it. And the way we standardize it is basing it off the hydrogen half cell, which is this bit over here. Okay. The way we can measure that is we're looking at using a voltmeter. That helps to allow us to measure the cell potential difference. We've got electric potential here, the standard potential, electrode potential. And as it's written there, we'll go into a little bit more detail out in a moment. That's the voltage due to the difference in charge on the electrode and the electrolyte compared to a hydrogen half cell. We're sort of doing it compared to this. It's a completely arbitrary decision, but when people started doing this is what they started to do, so they could work with something and keep it consistent. And it's all done at, as it's done here, it's under set conditions. It's just done a solution of 1 molar. And the pascals it's there if you want, and temperatures 25 degrees Celsius. And we say that the half cell for the hydrogen half cell is at a sign 0 volts, and that's sort of what's shown over here, where you can do that. And then so we're looking at here, standard hydrogen electrode is used for with other half cells so that you can measure against it. So if a species accepts electrons more easily than the hydrogen ions do, its electrode potential is positive, and if it accepts them less easily than the hydrogen ions do, its electrode potential is negative. And we're using that, so it's just a matter of relative numbers relative to that particular half cell, and from that we work out a cell potential differences. And good always, I like these tips. If a half equation has electrons on the reactant side, it's a reduction. So reduction is gain. So that's saying if I've got zinc 2 plus 2 electrons gives me Zn, so remember that's going to be aqueous, that's going to be a solid, then that would be a reduction half equation. All right. So the series, what is it? It's a series of chemical half equations arranged in order of their standard electrode potentials. Quickly, that is basically what it looks like. That is the data booklet, so that's one you should use for most things. I've got the book one here as a bit of an example. We'll bring that up in a moment. If we want to work out what the potential difference is we're going to generate under these conditions, we've got the E naught of the cell. That's what we want. We want to look at the oxidizing agent, so we want to look at whatever side we go from here and minus the reducing agent. So for example, that would be sort of like that. Okay, so we would pick, if that was the 2, I'll just pick calcium and the fluoride, we would look at say 2.87 minus, and but it's a minus, would be, in that calcium for example, it would be 2.87. That was quite lucky, and you would work it out like that. So that all of a sudden becomes 2.87 plus 2.87, and you'd get a number, and that's what your cell potential difference would be. Because remember, this would be the E naught for the oxidizing. Oops, my stylus is a little bit slow at the moment. Minus the E naught. Oops, I don't need to do it like that. Sorry about this. My stylus is currently a bit laggy. E naught of your reducing agent. Oops. Okay. Not very clear there. Sorry about that. Wasn't really going to write something there, but that's how you would do it. All right. That was a quick way. I actually have a more detailed way in a sec that you need to do. Sorry. Got ahead of myself a little bit there. So let's quickly have a look back at this. So data booklet, always use a data booklet. But the book example is useful just the visual of this, as in strongest oxidizing agent, strongest reducing agent. It's good to have that picture in there as a memory. Sorry, got slightly distracted by an email. So just to reinforce again, strongest oxidizing agent is up the top, strongest reducing agent is down the bottom, relative to what you're looking at, and that is important in a little bit later, and we'll see that why that's important a little bit later. All right, so when we're doing something like the Daniell cell, and it could be any of these cells, we're going to write the Haath equation occurring in the galvanic cell in descending order of electrochemical series. So for example, if I looked at where copper and zinc are, so copper is, let me scroll down. So if you, I don't know, you won't be able to see where my thing is. I'm literally going down to find where copper is. I'm looking for Cu2 plus here. So that's over there, and now I'm looking for zinc 2 plus, which is that one. So I'm looking for that. So keep in mind, strongest oxidant, strongest reducing agent, and that's in the order I've got them here. So they've done it deliberately. And if you had a look at their numbers here, 0.34 and minus 0.76. So one of those things is you need to look at, when you're looking at a cell, you look at what's present in your cell. And for example, you would have if you've got your cell like this, you know there would be, you got your Z there. You know that was copper here. I think we had zinc sulfate. So in here you're going to have Zn2 plus, and then here you would have copper 2 plus. Now it's not always going to be this simple in terms of what we're looking for, and we can see what we've got. So we've got essentially these parts here, but what you need to look for is the strongest oxidant, strongest reductant, and that's what you're looking for when it says these two bits here. So 3 and 4. Select the oxidizing agent with the highest EO. That's what I've just done. That's the copper 2 plus, and select the reducing agent with the largest EO, which I've done with the zinc. You need to balance out the electrons if required, and for this one we don't have to. And that ensures we can cancel it out. You write the full equation by adding the two reactions together. Now, I wouldn't add them like this. You would be going from something like Cu2 plus 2 electrons goes to Cu. Now, put units there. I'm just being a little bit lazy here, not doing that. Whereas a zinc would be going in the opposite way, going zinc 2 plus 2 electrons. Oops, I'm missing some things there. So plus 2 electrons. I can cancel those out from each side. Yeah, and so what I'm going to be left with is Cu2 plus Zn. Might as well put the units in now. S and Cu. That's a Cu, not a Ca. So my writing's not the greatest. It's a Cu solid plus zinc 2 plus aqueous, and that's write the full equation and determine the cell difference. Well, it's going to be EO of the one that's under. Remember, if we go back up to here, the oxidizing agent, that's this one. So it's going to be EO equals 0.34 minus, then I'm just going to, just to be clear, 0.76. Okay, and that would give you a value of 1.1 0.10 volts. You can put a plus in front if you need to. Okay, so that's how you can work through these questions. So this first bit here, okay, is basically what I said there. You're always looking for this, whatever species you've got available, you're always looking for the strongest oxidizing agent, so whatever's on the left, upper left, and what's on the strongest reducing on the lower right. So you're always looking in that sort of setup there. So here's an example that you can work through. You've got, these are, say for example, these are the species you've got. All right, so I've got some Fe3 plus and Fe2 plus, some H plus, some copper, some tin 2 plus, and some lead. Now, if I look at this, and that might be whatever I've got in my beakers and stuff. Now, my strongest oxidizing agent is that one, as I've highlighted there. What I've got present is my strongest reducing agent, which is the lead there. It's not this. I don't have that. I only have that. So I have to pick that one there. And that's where you would go, for example, 0.77 minus 0.13. Okay, and that would give you 0.9 volts as an EO. Okay, that's how you'd calculate it. A good way to remember this, I call it the backward Z. You're looking for a backward Z because it's shaped like a backward Z. So if I do it on this one up here, as you can see, that's what I'd be drawing. It's a backward Z. And what it means is when I'm on, let's go back up to here for a moment. Let's actually use a data booklet one because it's a bit cleaner. So for example, if I've got Ag there and nickel here, what I'd be writing is this reaction in that direction, and because remember it's a backward Z, and so this reaction would be written, so I'd be going something like, I don't know if this is actually a possible thing to occur, but plus electron goes to Ag. Again, I'm ignoring the states just for the moment. And then this one here, I had nickel. So I'm not going to write it as nickel 2 plus because that's not the way the reaction is going. The reaction would be going nickel is going to nickel 2 plus 2 electrons. And then I'll do what I need to based on that. But it's that backward Z configuration you need to work with. That's what I like to call it, the backward Z configuration. All right. And as it says here, another good tip when you're balancing things, just make sure we cancel out things that are common. All right. So that's what we talked about here. Write equation forwards, write equation backwards. All right. Okay, so let's have a look at this question. I've got Fe3 plus electron, give me Fe2 plus with an E naught of 0.77. Nickel 2 plus goes to plus 2 electrons, plus goes to nickel, and it's got an E naught of negative 0.275. So strongest, just to highlight, strongest oxidant. Okay, which means it's been reduced. This is strongest reductant. And therefore it's going to be being oxidized. Okay, so let's actually, it's not asking for this, but let's sort of draw a bit of a setup here, just because I can. You don't need to do colors in any of this. I like to just do colors because I can. Okay, Oops, wrong spot. I'm going to go over here. All right, so between those would be my salt bridge. Okay, then I've got that's my internal circuit, external circuit. Now I'm going to say this is the anode, just because I like it easier. This one's going to be the cathode. So at the anode, remember that's where oxidation occurs. So whatever's been oxidized, that's going to be the nickel. Okay. So and this one I'm going to have nickel solid goes to nickel 2 plus 2 electrons. That means the electrons are going to flow in that direction. So electron flow is that direction. So this would be my nickel. This here would be something that's inert electrode. All right. And I'd have to have in solution, I'd have to have Fe3 plus. Okay. Keep in mind that would go to here and produce Fe2 plus. All right. So that's sort of what's going on, because remember, as the nickel's in there, as the electrons are flowing out, coming off there is going to be, I don't know what's going to, nickel 2 plus. Okay. One of the things I forgot to mention earlier about this purpose of salt bridge as well is that it keeps the charge sort of even on both sides, and so that's another reason to it's important we have a salt bridge going through there. All right. What's next? So we've identified the anode to cathode. What's occurring at the anode and cathode? So the reaction here would be, here it's going to be Fe3 plus an electron goes to Fe2 plus. Again, with the proper states, you've got to make sure you put the proper states on there as always. So calculating the standard cell potential, we're going to go E naught equals the one that's been reduced, ER, let's call it minus E or O, it's going to be confusing there. So it's going to be 0.77 minus 0.25. Okay, so it's going to be 0.97, 1.03, so 1.03 volts positive. So that's what my E naught would be for that one. Sorry, slight correction. Clearly my maths was a little slightly off there. 1.02 volts. Not what to do for you. You should be getting those numbers. Use a calculator. Calculate that. Not try to do it in your head. So a couple extra questions here. Cell has this reaction as follows. Write the two half equations. So we're looking at, that's one. Sorry, I'll make it go back to full size again. Sorry about that. And then we're going to go red, zinc, and the zinc 2 plus going over there. So how would you write that? You're going to write Pb 2 plus aqueous. Now, because it's going in that direction, it's making I've got the electrons there. Plus, it's going to be plus 2 electrons. Gives me PbS. All right, and then for the zinc, you got sorry, getting ahead of myself here. You're going to be writing the zinc as a solid, and that's going to give you zinc 2 plus as an aqueous plus 2 electrons. All right. So if I had to draw, it says label anode and cathode, so let's draw this. So it's good practice to just get used to drawing these. Salt bridge, call it KNO3 is a nice one to always use. Okay, I've got my wire across there. Now, just because I like to put it over here, I'm going to put my anode over there and my cathode over here, which means electrons are flowing in that direction. Now, what's going to happen here is I'm going to have my zinc. So on this electrode, this half cell, it's going to be zinc goes to, so zinc solid goes to zinc 2 plus aqueous plus 2 electrons. And then you're coming across to here, so you're going to have the lead. You're going to have Pb2 plus in here. Again, you'd probably have a Zn2 plus here. Keep in mind, got a solution here. All right. Over here, you're going to have Pb2 plus 2 electrons. Gives you Pb solid. Don't forget the site, the states it's in. Okay, so we're going from electron flow this way. We've identified the polarity, which is negative. Identified which one's the anode. We've identified here positive as the polarity and it's the cathode, and what reactions occur at both. So you've done that. That's how you'd answer a question like that. Now let's have a look at this one here. Next question. It says consider following equations that appear in or shown in the electrochemical series. So this is just taking a snippet of electrochemical series, and it's giving you some things to predictions to make. Okay. So the purpose of a question like this is checking that you understand the electrochemical series and how it works. So if I've got Br2 and Mg2 plus, let's have a look at what I've got. I've got Br2 up here and Mg2 plus. If I've got those two, then there's not going to be any reaction occurring. There's no reaction because they're both oxidizing agents. Okay, I'd have to have, for that reaction to occur, if I've got Br2, I would have to have a magnesium solid. If I don't have that, not going to happen. All right, next one. I've got nickel 2 plus, so where's nickel 2 plus there? And I've got Br minus. I've got Br minus. In this case, again, no reaction. And I need you to think about when you're doing questions like this to work out why that would be occurring. Okay, and the reason for that is that the oxidizing agent NO2 plus is actually below the Br minus. So remember, to get this to work, I have to have that backwards. This has to be the oxidant, the oxidizing agent, and this has to be the reductant, the reducing agent. Okay, in this case, I've got like a normal Z. Don't want that. I need a backward Z. The oxidant has to be up there, and the reductant has to be down there. We don't have that set up, then there's no reaction. There's no spontaneous reaction going on there. If I've got nickel 2 plus and Mg, now I do have my backward Z, so the oxidant is higher than the reductant, then the reactions are going to occur. So does a reaction occur? Reaction occurs. And so you could actually work out, if you wanted to, what the equation would look like. You'd basically get the nickel 2 plus 2 electrons goes to nickel, and here you would have, remember, this reaction goes like that. I write it like that. This reaction, I write it like that. So in that case, the Mg goes to Mg2 plus 2 electrons. Okay, and what you'll see is you'll get cancelling of the electrons here, cancelling of electrons here, and I'm going to go nickel 2 plus, so nickel 2 plus Mg, and that's going to be aqueous, that's going to be solid, that's going to give me nickel solid plus Mg2 plus. And so that's what you can do. You can do other things with that and work out, you know, what your electric potential is, but we're not going to worry about that right at the moment. One last thing, I just realized as I was answering that last question that I didn't actually answer the overall equation. So what do I need to do for that? I'm going to have to go Fe 3 plus electron equals Fe2 plus. The next one here is going to be Ni2 plus 2 electron. Oh, actually, let me rephrase that. Let me write it as I need to write it here. It's going to be nickel goes to Ni2 plus 2 electrons. That means here I'm basically going to multiply everything by 2. And so what it's going to look like 2 Fe3 plus 2 electrons gives me 2 Fe2 plus. So now let me just script it for a moment. Got that, got rid of that. So now what I'm left with the overall equation here is 2 Fe3 plus nickel would give me 2 Fe2 plus Ni2 plus. This would be aqueous solid, aqueous. Okay, all right, that's it for this section.